All right, Physics 3030, the Universe. This is lecture 9, and here in this lecture we're going to start talking about the stars, and specifically the first set of stars. And we start with the dark ages of the universe, and then we'll talk about the classification of stars, which is populations of stars, and then specifically population 3 stars, which really describe the first generation of stars. Okay, so as you recall, talked a little bit about the inflationary period in our last lecture. Okay, that's this exponential expansion that the universe underwent very early on. We talked about the early universe, so we sort of talked about the area from the Big Bang till about the CMB, and then we've talked about the CMB, the cosmic microwave background radiation. That's the light that we can still see the remnants of, and this is a neat picture because it really has the CMB radiation in here. Okay, so now we've gotten to recombination, and now we're in a period where we have helium and hydrogen, and helium's about 25% of the stuff, hydrogen's about the other 75% of the stuff. And by stuff here I just mean the baryonic matter, right? We'll start talking about dark matter and dark energy here soon, and this really only makes up a small portion of what we know has to exist in the universe. But anyways, this is that stuff. Those are the proportions of the baryonic matter, which is the stuff made of baryons. Okay, now what we want to do today is get us from this recombination period to the first stars and talk about this early period of stars. Okay, and the dark ages are really just this area, this part of history of the universe where there's no real light, right? Because the photons have been absorbed. There's light from the CMB that's floating around, but there's no stars giving off new light. Okay, and we go from this time when there's in the dark ages to a time when there's all kinds of structure that we see. Okay, and a good. Let's move to the next slide here. This is one of the most impressive, I think, pictures that the Hubble Space Telescope has ever taken. This is the ultra deep field view. And it is a view in a certain part of the sky that uses multiple cameras to take a very long exposure picture of the universe in one direction. Okay, and at first glance this might look like a bunch of stars, but notice that there's spiral structure to some of these. There's another, you can sort of see the spiral structure in this one, and you can look at really, really good pictures of this online if you search for the Hubble Ultra Deep Field, which I'm imagining this video is not doing it justice, but you can see all kinds of little structure in this ultra deep field. And these are all galaxies, right? Think about this. Most of the stars we see in the sky are in the Milky Way galaxy. And so all of those stars, there's just as many stars in one of these galaxies as there are in the Milky Way. In fact, a lot of these galaxies are a lot bigger than the Milky Way. So all of this structure, the galaxy structure and everything, came from this period after the CMB, after the cosmic microwave background radiation was emitted, from this very, very uniform mix of hydrogen and helium. Okay, and so we're going to sort of start talking about how this came to be. But this is just one of the most impressive pictures to me personally. There's so much structure, there's so much diversity, and there's so much stuff besides us out there. This is one of those pictures that just is absolutely humbling from astronomy. Okay, so clear that, and so now we've got a blank sheet here. What I want to talk about is how we go from this uniform structure, which I sort of want to just model, right? The idea is that this is not exactly how it is, right? The atoms are all moving around, but it's pretty uniform. And you go from a structure where all of the atoms that you have are sort of pretty uniform, to something where you have clumps. You know, you have clumpy galaxies and stars, right? These are not to scale, obviously, but I have a very clumpy structure, okay? And what it is, you know, in that 1 in 10,000th fluctuations of the CMB that I've been talking about a lot, some of these dots over here are closer than others. And so these two dots maybe are closer, and they feel a gravitational pull towards each other that's stronger than the pull that these two feel. Okay, so these blue arrows are bigger than those red arrows, so what ends up happening is those two dots get closer to each other. Those two dots get closer to each other, and they start to clump up. Okay, and this is what gravity gets us. All of this structure starts from gravity and those little tiny fluctuations that we see. Okay, and we'll talk about actually how a lot of this structure, it's necessary to have dark matter to have the structure, but we'll talk about that when we start talking about dark matter as well. Okay, so that's sort of the gist of what we're going today. So the first population of stars that we really want to talk about is, are actually called the population 3 stars. Okay, and so I'm going to talk a little bit about how we categorize stars. First of all, a little bit about how stars form. Okay. Stars form by this clumping of matter that we were just talking about. And what happens is there are two simultaneous forces that are sort of working towards each other. One is that you get that gravity working, and you start getting molecules that are hanging out near each other, right? So this is sort of a clumpy bit of molecules. And all of these are moving around in all kinds of different directions, okay? And they all have energy, sort of random, chaotic energy. And so there are two types of energy that we see. One is gravitational, and the other is this thermal energy. And the thermal energy, right, is the energy of just the random energy of all the molecules bouncing off of each other. Okay, and as we've already talked about, right, the gravitational energy pulls everything together, and the thermal energy has the tendency to keep the molecules, or in this case really just atoms, or depends on what we're talking about, right? Helium just occurs as a single atom. Hydrogen always comes as H2, so keep molecules apart. Okay, and you can imagine that because just everything's bouncing off each other. As they get too close, they bounce off each other, and as they get closer and closer, what happens is it gets hotter and hotter, right? So these two forces work sort of together, and so the gravitational energy starts pulling these molecules closer and closer together. As they get closer and closer together, they bounce off of each other more and more, and what ends up happening is the gravitational energy, some of it gets turned into this thermal energy. Okay, and there's this interesting limit. Okay, and it's called the gene's mass. It has nothing to do with Levi's, okay, or Lee Cavaricci's if you're into the early 90s. The gene's mass is a limit of how much stuff you can have before the matter collapses. And by collapses here, I really mean collapses into a star, right? So we're talking about not collapsing into a black hole. We'll talk about that later. But there's this limit called the Jeans mass, and there's a Jeans length that's in your book. The Jeans length is equal to the velocity of sound in whatever you're looking at, divided by g, which is a constant of nature, times rho, where rho is the density of the stuff. So let me annotate this. Rho is the density of the gas. Vs is the speed of sound in the gas. And G is called Newton's gravitational constant. Okay. And what happens is actually at some point you get sound bouncing across this big clump of gas, and the sound causes compressions, and those compressions just trigger a chain reaction that makes everything start to compress into a star. Okay, and so the idea here, the story goes, is that we get some amount of thermal energy. The gas starts heating up, and what happens is, as it heats, it starts pushing back, right? So it gets to some point, it gets hot enough that the thermal energy is big enough to sort of balance the gravitational energy. Okay, the pressure from the thermal energy balances the gravitational energy in some sort of stasis. But now you have this big chunk of matter, right? So let's see. What do I want to do? Erase some of this stuff. Okay, you have this big chunk of matter up here. Okay, but there's still other molecules coming in. Okay, and as those other molecules come in, right, you have more gravitational energy because you have more mass coming in, and then you have more thermal energy because the stuff is heating up more, and it's still trying to balance out. And what the Rayleigh jeans, the Jeans mass is the limit of how much stuff. So once I reach the certain critical amount of stuff, then I collapse into a star. Okay, and what happens here is the gravitational force, because there's so much stuff, gets strong enough to overcome the thermal energy. Now, there's a big point here that your book makes that I want to talk about, which is that cooling of the gas is really important. If the gas sort of cools off really easily, okay, so easily cooled gas collapses faster, because as it cools, just giving off energy to others, that what happens is, right, you get gravitational energy turns into thermal energy, and then that thermal energy just radiates away. Okay, it can radiate away, and just like a hot cup in a cold room radiates away. And if it cools fast, then you lose that thermal energy that's fighting gravitational energy, and it collapses. Okay, so easily cooled gas collapses faster, and then insulating gas, so stuff that doesn't cool very fast, it takes longer. So it collapses with only more, let me write it a different way here. Insulating gas takes more mass to collapse. Okay. And this is going to be the basis of what we talk about, okay, today, with the different populations of stars and where we get those. And I want to make a point here that this balance, so the balance of gravitational energy and thermal energy really dictates the evolution of stars. Okay, and sort of out of the breadth of this class, but just to touch base with it, when we start talking about supernovae and the evolution of stars, what ends up happening is they end up burning up all their nuclear fuel. And when they burn up their nuclear fuel, they don't have as much thermal energy. And so then the gravitational force takes over, and then they collapse in on themselves. When they collapse in on themselves, a lot of times things get close enough so that a different thermal reaction starts, a different nuclear reaction that needs more heat to get started, will start again. Okay, and then that runs out of that fuel, and then the star collapses in on itself again, and this keeps going until some point when maybe there's no fuel, or in special cases it'll collapse. And when it collapses, it gets to a point where it causes such a huge reaction that everything kind of goes at once and it explodes, and that's what a supernova is. Okay. And if you guys have questions about stars, there's great resources online, and if you have questions, you can ask me about it, but that's not sort of in the breadth of this class. So the next thing I want to talk about is sort of this one different way of classifying stars, and that is by population. So populations of stars. Okay, and this scheme is due to an astronomer named Walter Bande, and he started categorizing stars into different populations. And this categorization ends up having to do with the age of the stars, actually. But it really came about by which stars he saw first. And by he, I mean all astronomers, really, right? So population 1, Pop 1 stars, okay, are they have heavy elements in them, so they have like carbon and even heavier elements than that. Heavy elements. They're young, and they're near to us. And by near, I mean they actually exist in the arms of galaxies, because if you don't know, we're in the one of the arms of the Milky Way. Okay, and this happens to be where these population 2 stars appear, and these are actually right here. They're actually the youngest stars. Okay, and they're called blue stars. There are a lot of blue stars, and that just means what sort of range of light they give off. Okay, and then there's population 2 stars, okay, which, as you can imagine, they're just the second ones that we really saw, okay, and they have sort of medium elements in them, I'll say. So they have like beryllium and lithium in them. All of them have hydrogen and helium. All of these stars, that's their first main fuel source is hydrogen, okay. So they have medium elements, and these are medium age. Okay, so they're older than the population 1 stars, and these actually have, I should say this, much more hydrogen and helium than population 1 stars. They really are dominated by this hydrogen and helium. So they have some medium elements, but they're really dominated by those. Okay, and they're older than the population 1 stars, and they're found in the bulge of the galaxy. Okay, and that's far away from us, and so that's why they were seen second. And there's a lot of red giants in here. Okay, and then there is a third set of stars that has never been seen, okay, but we're going to talk about a lot today. They're called population 3 stars, and they would have no elements but hydrogen and helium, which was what was in the original well, that was what was in the universe when these stars started. Now remember, there's tiny trace amounts of lithium and beryllium, but these stars are really mostly hydrogen and helium. That's all that really is there, and they are the oldest stars. They would be the oldest stars. Now, I think it's really important to note, right? Not yet seen, and we'll talk a little bit about that and how we do know that there's evidence for them. Okay, and they might not even be in galaxies, right? Galaxies need stars to form, so these stars would form and then maybe galaxies would start around them, and if we can see far enough back in time to see these stars, they might not be associated with galaxies, or they'll be associated with elliptical galaxies, but not galaxies that have the structure that we see today. Okay, and so we've actually sort of built population 3 stars from computer simulations. So starting with what we know about the composition of the universe way back in the day, we can use computers to simulate what a population 3 star would look like. And the idea, so the neat thing about these stars is because of some of the chemistry of hydrogen and helium. So hydrogen and helium are bad conductors of heat, and this is especially compared to the heavier elements. Okay, so if we're looking at stars that are made exclusively of hydrogen and helium, okay, then we know that the hydrogen and helium are bad conductors, so the thermal energy that I was talking about earlier is not given off to space as readily. And so what ends up happening is the Jeans mass for a star that has a bad conductor in it is much larger. Okay, and it's much larger because the hydrogen and helium are bad conductors. Okay, so what does this mean? This means that if I go to a computer and simulate with the Jeans mass what a population 3 star would look like, they range anywhere from 30 times the mass of the sun to 500 times the mass of the sun. Okay, and this is huge. These are huge, huge stars, and this is really how big they are, how big they need to be for ignition, right? So this is sort of the point of what I was talking about earlier. When they collapse and get the force of gravity sort of collapses them into something big, collapses them into this smaller space, all of those molecules get so close to each other that the thermal energy is enough to start nuclear reactions. That's the whole gist of what I was talking about. I might not have made that point very well, right? So the heat is enough. This is for all stars. Reaction. Okay. But because these have such bad conductors, they can be up to 500 times the mass of the sun. And there are two really important things that we get from this, two important conclusions that happens. One is that because they are so much bigger when they form, they burn really hot and give off ultraviolet radiation that would actually ionized the nearby hydrogen, right? So we have these hydrogen molecules, and hydrogen comes usually as a molecule with two of them attached to each other by molecular bonds. And this ultraviolet radiation, remember this back and forth we have of if I have a sort of two states around an atom, and I have an electron, right? An electron up high, and it jumps down, it emits a photon, right? Or if I can have it happen the other way, where a photon comes in, right, and makes an electron jump up, and it can jump up so that it's even free. Okay, these are sort of the two different cases. Well, that's what ionization is. I hit this electron over here with enough, with a photon of enough energy. Boom! It knocks it off of the atom, and now I have protons, bare protons, and bare electrons around. Okay, and the interesting thing about this is that now there's this CMB, this cosmic microwave background radiation, and it's sort of just floating around, right, waiting for us to discover it in the 60s. And when you have ionized hydrogen, ionized gas of any kind, it polarizes light. And you guys are all familiar with the word polarized because of polarized glasses, and it just means that, you know, the way the wave of light is oriented, it becomes really specific. It makes it all sort of turn in the same direction. Okay, and we can see remnants of this. We can see remnants of this, and so this is where we know this points to the existence of these population 3 stars. Okay. One of the places where this ionization, where this polarization is seen is actually in the CMB, right? So we see this in the CMB, and specifically in WMAP, the WMAP satellite data. We see this polarization. It actually requires pretty early population 3 stars. All right, and there's one more thing I want to talk about here. And that is the other thing that happens with these population 3 stars is that we get something called hypernovae. Okay, and this is hyper here just means bigger than super, right? So a regular supernova, again, is that star sort of runs out of fuel, the thermal energy isn't enough to hold everything out, so it collapses in on itself. When it collapses in on itself, it gets more thermal energy, and then there's enough thermal energy to start a nuclear reaction that just takes off so fast that it causes an explosion. And hypernovae, this collapse, right? So this is the idea, is that these stars are so big that this collapse has enough energy for pair production. Remember from our talk about particles, right, where you have a gamma, I say gamma, that's the symbol for light. So you have a photon coming out, and if it's high enough energy, it can actually give off 2 particles, so like an electron and a positron. So this is what we mean by pair production. So you get enough energy that the photons that are produced have enough energy to pair production, and it's just this crazy giant explosion that we don't see because there's no stars big enough to do this anymore. And these explosions produce heavier elements. Okay, and it's really in nuclear chains. So these produce the heavier elements, which then help to produce the next generation, or here population of stars. So this would be the population 2 stars. Okay. And the idea is that the population 2 stars, they have a little bit heavier elements. Those heavier elements cool faster, so it doesn't take as much stuff to reach this critical Jeans mass for what it's made out of to collapse into a star. So we get smaller stars after this. And these hypernovae are just crazy big. Okay. And then some of these are big enough. Well, it's not big enough, but some are. Just put it this way: some produce what we call supermassive black holes. So in some simulations, depending on the right conditions, and this happens a lot of time with some supernova, your book will say these hypernovae basically just blew themselves apart, but in some special conditions they can actually produce black holes, and since they are so big to start with, they're much bigger than the black holes we see on the stellar mass range, the sun's mass range. And we'll talk more again about black holes in I think next week actually. So some of them start the seeds of these supermassive black holes, which will become really important because that's what happens to be at the center of different galaxies. Okay. All right. So let's see what else I wanted to talk about here. So that's it really for these stars. And now we get more production from different stars, from these population 2 stars and the population 1 stars that we know and love and see have even heavier elements in them. They don't have to be as big to form even as the population 2 stars. Now, just a quick interesting bit about stars that we can know is that fusion, which is the type of nuclear reaction in stars that happens, right? Can only really make iron. So it can go from, I can start with hydrogen and I can go all the way up the chain of elements to iron. Iron is, the symbol for iron is Fe, right? Okay. And this has to do with some quantum mechanics, something called binding energy, yada, yada, yada. But that's all you really need to know. It's because of quantum mechanics, the only way that I can get energy out of these reactions is by going all the way to iron. Now, of course, we have elements bigger than iron, and where do those form? Those all form in either hypernova or supernova. There's enough energy because of these explosions. So novae produce the elements that are heavier than iron. Okay, and we all have elements in us that are heavier than iron, and we have even iron. Well, we have lots of iron. We have things that are less heavy than iron as well. Everything that we're made out of a lot of carbon. We have a lot of oxygen in us, a lot of nitrogen. All of these things had to have been made in stars. So this is the idea, right, that we are stardust. We are sort of the ashes, really the ashes of nuclear reactions. Okay, that's where this idea comes from. They talk about it a little bit in the beginning of your book. So this is sort of the deal. So fission happens. Fission is this other. Fission, I think, is with 2 S's. Fission is what gives us the heavier elements than that. Okay. Oh, I do have just one more thing here. Let's see. Is that I have a picture, and I have given you guys a website to take a look at. But this is a picture of these population 3 stars getting started, and what this is supposed to be is sort of waves of the ionization as the UV radiation is given off by these stars. into the surrounding area. Okay, basically ionizing all of the gas that was in the universe until it gets to cool down enough to give off, or until it cools down enough to attract those electrons again. Okay, that's it for this lecture. Thank you.